Now let's take a look about a very interesting application of the plane mirror. So this is the so-called corner reflections. So let me try to first define what is the corner reflectors. So here you can see the three plane mirrors, and they are joined at right angles together. So what happens is that this kind of the corner reflectors behaves in the 3 dimension the same as the two mirrors at right angles in 2 dimensions. So therefore, a ray incident on the corner reflected is set back in the same direction from which it comes. So for example, here, if you only look at the 2 dimensional of these structures, so the incident light will hit on the first one, be reflected, and interact with the second one, be reflected. And you can see now, the direction of the reflected light actually is parallel to the incident light, just in the opposite directions. So no matter what kind of light, when they enter and interact with the corner reflectors, they all follow the same principle. All the reflected light actually will be going back into the same direction of the original direction it comes from. And this kind of behavior can apply to many useful applications. And one of the most interesting one is this one. This is a device we put on the surface of the moon. So this happens when the Apollo's missions 11, 14, and 15, the astronaut put a retroreflectors arrays, which is this one. And these arrays consist of the 100 corner reflectors on the lunar surface. So now the scientists on the surface of the Earth can set a laser beam and to the appropriate location on the moon. And this position is where the retroreflectors will set it back to the source. And therefore, by doing that, we can measure the round-trip travel time of the light. And the scientists can determine the Earth and Moon distance to a very accurate value up to 3 centimeters. So it is a very precise measurement. And the error is simply just the 3 centimeters out of the total distance, roughly the 385,000 kilometers. So that is one of the very useful approach. We can measure the distance between the moon and the Earth. And this is a telescope we use to launch a laser beam and receive the laser beam, the reflected laser beams. And intrinsically, the only thing you have to know the physics behind for this is the corner reflected, made of 100 corner reflected, and the laser beam will hit on this one and be reflected, and the direction of reflected light will also parallel to the directions. Why it is useful? Now we can, by this kind of property, the incident light and reflected light are parallel, we can assume the distance traveled are the same. That is reason, by knowing the distance travel is actually 2 times the distance between the moon and the Earth, and we also know that the light is moving at the speed of light. So by measuring the time difference, then you can calculate the distance between the moon and the Earth. Now let's try to take a look about the second kind of the mirrors. It is a so-called a spherical mirror. So apparently the shape is a sphere, but it depends on which end of the mirror is mirrored. So when I say it is mirrored, I mean that they will put a piece of the material such that the glasses is no longer transparent. When the light interacts with the surface, they will be reflected. So it depends on which end of the spherical surface is mirrored. So if it is the outside of the surface is mirrored, then we call that it is convex. If it is the inner side, we call them it is concave. So let's take a look about this one. So if you has the inner side is mirrored, we call this is concave, and if it is outer side, we say this is convex. But before I define more rigorously about the two different types of the spherical mirrors, we first have to define a very important thing, is that the central axis. So this central axis is actually from the center of the sphere surface, and they will reach to the center of the curvatures. So what does it mean? This line can help you determine how curved the spherical mirror it is. And then you can also determine that now, because this is center of curvature, yeah? So you can basically say that now the distance from the C to the surface of the mirror are all the same, no matter to which point. So you will see that now the second, let's try to focus on the convex mirrors first. So now you have the parallel rays hitting on the spherical mirror, and now this is convex. So you can see now all the light, incident lights, are parallel to each other, and they will be reflected. So the law of the reflection is still respected. So for example, this one, they will hit on the surface, and what is the normal lines? So actually, the normal line is the dashed line perpendicular to the surface of the convex mirror. And you will find out this dashed line, if you trace them backward, actually, the normal line is the line connected to the curvatures. So because the curvature is the point, it will have the same distance to the surface of the convex mirror with the same distance, which means it is behaved like the center of the spherical surface. Yeah? So it is definitely also perpendicular to the surface. So now the light will be reflected. And now if you trace the reflected light backward, also again, you will find out all the reflected light can be traced backward, and they will gather at the same point. And this point where the reflected light gather together is the so-called focal point. And for the mirror, which is convex, the focal point is behind the mirror. So what then? There's a very important properties now for the convex. So we know that now the incident light is parallel, and they will be reflected. And now this reflected light, when you trace them backward, they will go to the focal point. This is what we just mentioned. So now let's try to study one by one. So this incident angle will have angle theta with the normal line. But because the normal line is also the line connect to the curvatures, so we know if this is angle theta, this one should be also theta. Now let's take a look at about the second one. The light will be reflected by the surface, and the reflected angle should be also the theta because the law of the reflections. Now you trace the reflected lines backward. Then you will see if this is theta, then this is also the theta. So therefore, for the triangle AFC, these two angles are both thetas. So what does it mean? It means that the distance AF and FC are the same. So this triangle has two sides with equal lengths because the angle is the same. And now let's try to assume that the distance from the C to the point A, which is basically, you can think it in terms of the radius, which is r. Then if the theta is very small, then we can basically approximate that is the length AF and FC is basically just 1/2 of the radius. Okay, FC is just 1/2 of the radius. And you'll find out actually FC is also the same as the focal length. So therefore now we can determine the focal length, which is just 1/2 of the radius of the curvature. But here I put additional 1, which is the negative sign. What does the negative sign mean? It simply just reminds you that the focal point is behind the mirror. The focal point is behind the mirror. And for sure, R is the distance. So SI unit for the focal length is also meters. So this is for the convex mirror. So now let's take a look about the concave. So this is a concave surface. So you have also the parallel incident light, and the light will be reflected. So the light, for example, this one, they will be reflected to these directions. And how did you determine the angle? You should draw a dashed line which is perpendicular to the surface, yeah? And this dashed line also connect to one point, which is the so-called curvature center. And now you will find out that all the reflected light, once again, they will gather at the same point, which is the focal length. So you will have the center of curvature again and the focal length. But now the focal length is in front of the mirror. But all the relation we introduce in these convex mirrors, the angles and the distance between the R and F should be still the same, except now the focal length is in front of the mirror. So now the focal length is 1/2 of the radius of the curvature, but it is positive because now the focal length, the focal point is in front of the mirror. So now you know the difference between the concave and convex mirror. Now let's take a look about the quiz 3 today. So if you have a concave mirror with a radius of a curvature of 20 centimeters, then how big the focal length will be? And the answer is C, because we know that the focal length is 1/2 of the radius of the curvature, and because it's concave, so it is positive, so therefore it is 10.